U.S. Power Market Investment Note. What Microsoft's gas power partnership says about America's power gap. Microsoft and Chevron's Project Kilby in West Texas is a useful snapshot of how the U.S. power market is changing. In June 2026, Microsoft said it would build a new data center campus in Pecos, Texas, with roughly 2 gigawatts of planned incremental capacity. Chevron is arranging about 2.67 gigawatts of natural gas generation capacity. The two sides signed a 20-year power agreement, initially using behind-the-meter supply, with key equipment including GE Vernova large gas turbines and solar turbines equipment from Caterpillar. This is not yet a fully converted revenue number. First power is still broadly after 2028, but the project already makes the core point clear. Compute expansion can no longer route around reliable power. America's power gap over the next few years probably will not look like the whole country going dark at once. It also is not simply a story of total generation being too low. The pressure is more likely to appear first in specific regions, specific years, specific voltage levels, and high reliability loads. AI data centers, advanced manufacturing, industrial electrification, and extreme weather peaks are lifting demand at the same time. Older grids, substations, transmission lines, and long-lead equipment cannot expand at the same pace. In the short term, natural gas becomes the practical bridge. In the medium term, electrical equipment, substations, transmission, distribution, and on-site power systems enter a longer construction cycle. In the long term, the U.S. power market shifts from selling kilowatt-hours to delivering power that is reliable, connectable, and dispatchable. For roughly 2 decades, U.S. electricity demand did not grow at a sustained high rate. Offshoring, efficiency standards, and better lighting and appliances offset part of the load growth that economic expansion would otherwise have produced. Utilities, equipment makers, and contractors built capacity around low growth and replacement demand. Transformers, switchgear, distribution equipment, and construction crews were not designed for a sudden wave of large, concentrated loads. Now the demand curve is steepening, while the supply side still carries the rhythm of the old era. That is the deepest background to the power gap. The interesting part of Microsoft's Pecos project is not that Microsoft has suddenly abandoned renewables. It is that the delivery sequence has changed. In the old data center conversation, many people started with land, buildings, fiber, servers, and GPUs. Now the first questions are whether power can be connected on time, whether it can be supplied reliably after connection, and who is responsible when something goes wrong. Microsoft remains a major buyer of renewable power, and it will keep building low-carbon supply. But when an AI factory needs to come online on schedule, the scarcest items are often reliable capacity and interconnection speed. Chevron is not just selling a molecule of gas here. It is trying to sell a supply arrangement that lets a campus start on time. Fuel, generation equipment, the on-site power system, and a long-term offtake contract are bundled together. Traditional oil and gas companies used to be tied mainly to commodity price swings. Now, some of that capability can be turned into longer duration, steadier infrastructure service revenue. The value of gas in this chain is not only the fuel itself. It can also bridge part of the reliable capacity gap before new transmission and large substations are finished. Capital is also starting to read power assets differently. The Financial Times has noted that AI and data center power demand pushed U.S. power and utility M&A to historic levels. In the first 5 months of 2026, the transaction value was about $203.6 billion. Data center-related investment also increased meaningfully. That number should not be overread by itself, but it does show that assets once treated mainly as defensive, dividend-paying, rate-sensitive utilities are, in some transactions, becoming land, interconnection rights, and capacity gateways for AI factories. The scarce asset is not always inside the server hall. Often, it is outside the building. The demand-side change is no longer just a market theme. Lawrence Berkeley National Laboratory frames the turn clearly. U.S. data centers used about 176 terawatt-hours of electricity in 2023, or roughly 4.4% of total U.S. electricity use. By 2028, that could rise to 325 terawatt-hours to 580 terawatt-hours, or about 6.7% to 12.0% of the total. The range is wide, which means the forecast is uncertain, but the direction is difficult to ignore. Data centers are no longer a small subcategory of commercial load. They are starting to affect grid planning, capacity markets, transmission and distribution investment, and local politics. An AI data center is not an ordinary office building. It has a high load factor, high power density, and sensitivity to outages and power quality. It also brings heat rejection, water resources, and backup power into the site selection problem. In the past, 5 to 10 kilowatts per rack was enough for many deployments. Today, 50 to 150 kilowatts per rack is becoming a common part of the discussion. The 500 kilowatts or even 1 megawatt rack ideas discussed by OCP, NVIDIA, and Schneider show that this is not merely A bit more electricity. The power architecture and the thermal architecture both need to be redesigned. A 500 megawatts data center means very different things in different regions. In PJM, especially Northern Virginia, it runs into capacity markets, transmission constraints, and local distribution pressure. In ERCOT, it looks more like a test of real-time power prices, hot weather peaks, natural gas, and storage flexibility. In a vertically integrated utility region in the Southeast, it can become a regulated asset base and state rate case question. In Arizona, Nevada, and Utah, water, heat, and cooling may become the first constraints. In the Pacific Northwest, low-carbon power and cooling conditions are better, but community resistance, transmission, and local rates still matter. Electricity demand can rise nationally, but money and projects are realized one local market at a time. Outside the United States, the same pressure appears in different institutional forms. Europe is more constrained by grid connection, permitting, land, community resistance, and power price politics. Ireland, the United Kingdom, Germany, and the Netherlands have already been debating data center access and grid carrying capacity. China is more inclined to move compute toward regions with abundant energy resources through national planning, with Western renewables and ultra-high voltage lines as one answer. The Middle East is trying to combine natural gas, solar power, water resources, and sovereign capital to turn compute into a new form of energy export. The institutions differ, but the pressure is similar. AI is not contained inside cloud service companies. It is pushing its burden into the power system. Back in the United States, the most practical source of new power in the short run is still natural gas. It is not a perfect answer, and it does not solve every carbon constraint, but it can provide dispatchable, scalable, and relatively buildable, reliable capacity. That is why structures like Project Kilby appear. Nuclear power is the more strategic line. Life extensions, restarts, and small modular reactors will all matter to large cloud buyers because nuclear is closer to around-the-clock low-carbon power. But the amount of new nuclear capacity that can arrive within 5 years is limited. Wind, solar, and storage will continue to grow and remain essential over the long term. Yet intermittency means the system also pays for storage, frequency regulation, reserves, and transmission. The answer to the power mix is not a single choice. The more realistic combination is this. Gas fills part of the reliable capacity gap first. Nuclear carries the longer-term low-carbon baseload imagination. Wind and solar plus storage keep expanding. Transmission and substations move power closer to the load, and behind-the-meter systems deliver stable electricity into the racks. The short, medium, and long-term clocks are different. Project developers will choose based on delivery time. A solution that can turn on sooner receives a short-term premium. A solution that can lower carbon and system cost over time continues to expand later. The easiest place for this cycle to get stuck is often not generation, but delivery. Between a project announcement and actual power on, a developer must pass land and community review, transmission interconnection, substations, long-lead equipment, the power supply stack, behind-the-meter systems, cooling, and water resources. If any gate gets stuck, the gigawatts in the press release do not become real megawatts. When studying data center projects, announced capacity is only the starting point. The better question is where the project sits in the process. Waiting in a queue, past engineering studies, with capacity locked, with an ESA or PPA signed, with equipment ordered, with a substation under construction, or actually energized. Equipment is one of the most practical gates in this cycle. Large power transformers, generator step-up transformers, medium-voltage switchgear, high-voltage breakers, and electrical houses cannot be restocked like generic industrial goods. They require grain-oriented electrical steel, copper, insulation materials, high-voltage testing capability, skilled installation crews, and utility certification. Many projects are not missing an abstract thing called the grid. They are missing one qualified transformer, one certified switchgear package, or one substation design that passes testing and protection coordination. Equipment delivery is not a background condition. It is the power-on timetable. Transmission is even slower. Reports from Grid Strategies and ACEG show that new U.S. high-voltage transmission completed in 2024 was far below long-term need. A commonly cited public number is about 888 miles, while annual need for high-capacity transmission could be close to 5,000 miles. The United States is not incapable of building transmission. It has built faster in the past, but permitting, cost allocation, interstate coordination, and community resistance make transmission slower than generation today. Institutions are also being pushed by engineering pressure. In June 2026, FERC issued large load integration show cause orders to 6 RTOs and ISOs. It asked them to explain or modify rules around large load interconnection, network upgrade costs, co-located generation, interruptible load, and resource adequacy. These filings are not just regulatory news. They affect who pays for data center interconnection, whether ordinary customers absorb grid upgrade costs, how much project developers must prepay, and whether behind-the-meter generation can bypass part of the queue. They also affect site selection and utility capex recovery. The United States does not have one unified national grid. Physically, the classic chain is generation, transmission, voltage step-down at substations, distribution, and end use. But ownership and dispatch are spread across investor-owned utilities, municipal systems, rural co-ops, independent power producers, transmission owners, and regional markets. PJM, MISO, SPP, CAISO, ISO-NE, NYISO, and ERCOT are part dispatch center, part wholesale exchange, and part open transmission platform. A nationally rising load ultimately enters many local rules and regional prices. PJM is one of the most important windows to watch. It covers a large part of the eastern and mid-Atlantic United States, including Northern Virginia, the world's densest data center cluster. Data center pressure can show up at the same time in load forecasts, capacity prices, transmission planning, RTEP, tariffs, and large load interconnection rules. PJM is not all of America, but it shows one key transmission mechanism. When high-reliability load concentrates in a region, the power gap first turns into capacity prices, interconnection rules, equipment queues, and local politics. Cost allocation will become more sensitive. Data centers bring tax revenue, jobs, and investment, but transmission, substations, backup capacity, and grid reinforcement may eventually flow into ordinary customer bills. State regulators and local communities will not accept that transfer automatically. Large load tariffs, take-or-pay contracts, minimum load commitments, higher interconnection deposits, interruptible service, self-supply, storage, and load curve disclosure will gradually move from special clauses into normal negotiation. Project Kilby shows one path. The large customer pays for part of the incremental supply and infrastructure in exchange for speed and certainty. The supply chain tension has not disappeared. The United States wants to keep data centers, grid equipment, and critical energy manufacturing as local as possible. But storage cells, inverters, solar modules, power electronics, copper and aluminum processing, some medium and low voltage equipment, cooling system components, power semiconductor packaging, and some transformer materials still depend on global supply chains. The more urgent the expansion becomes, the more visible this tension gets. Policy wants more of the chain onshore, while project sites still need global supply to arrive on time. Tariffs and industrial policy can change the cost curve, but they cannot instantly create qualified capacity. Water and community acceptance will matter more. As AI rack density rises, heat rejection and cooling design directly affect site selection. Water-stressed and hot regions will resist evaporative cooling more strongly. Communities will care about noise, cooling towers, transmission lines, substations, and power bills. Microsoft's public description of PECOS emphasizes closed-loop cooling, non-potable water, and not drawing power from the existing public grid. Those details show that permitting a large data center is not only an engineering question, it is also a community question. Moving down the value chain, the closest medium and long-term bottleneck still sits in primary equipment and the grid side. Large power transformers, generator step-up transformers, high-voltage switches, breakers, substations, electrical houses, medium voltage distribution, bus bars, and cables have long lead times, slow certification, and limited substitution. Hitachi Energy, Siemens Energy, GE Vernova, Eaton, Schneider, ABB, Hubbell, nVent, Prysmian, and Nexans represent different businesses from grid equipment to distribution and connection. These should not all be placed in the same basket just because they touch electricity. Generation and power resources follow a different logic. GE Vernova, Siemens Energy, and Mitsubishi map to gas turbines and large power equipment. Caterpillar and Cummins map to reciprocating gas engines, backup power, and on-site generation. Bloom Energy maps to fuel cells with a pitch that it may shorten the waiting time between planning and actual power supply. Constellation and Vistra look more like platforms with usable power resources, capacity price exposure, and long-term customer contracts. Chevron's entry suggests that oil and gas companies may also sell more than gas molecules. They can bundle gas, equipment, and long-term supply arrangements into a more certain power service. Cooling and thermal management should no longer be treated as backroom data center equipment. CDUs, cold plates, dry coolers, chillers, pumps, valves, quick connects, and monitoring systems become part of the platform design as rack density rises. Vertiv, Modine, and nVent are not interesting only because they sell liquid cooling products. The bigger question is whether they can combine thermal management, power management, field integration, and service. Storage, microgrids, and flexible resources handle peak shaving, backup, frequency regulation, and load shaping. Fluence, Tesla, GE Vernova, Eaton, Powell, and Flex each sit in different positions. Utilities and power resource platforms are closer to holders of approvable grid capacity. Dominion, NextEra, and Southern benefit from regional monopoly positions, regulated asset bases, and long-term CapEx recovery. Their pressure comes from power price politics, CapEx approvals, and customer backlash. Constellation and Vistra are attractive because of dispatchable assets, capacity prices, and large customer contracts. They also face fuel, regulation, retirement, and reinvestment risks. Pull the time horizon apart, and the story becomes three clocks. In the short run, the shortage is reliable capacity that can connect quickly. So natural gas, on-site generation, backup power, storage, and interruptible load arrangements matter first. In the medium run, the shortage is equipment, substations, transmission lines, EPC capacity, and local permitting, so power equipment and grid construction move into a longer development cycle. In the long run, the shortage is institutional capability. Power markets need to pay in advance for reliability, flexibility, transmission, and load management. Real-time prices alone cannot build enough generation and grid capacity several years ahead. So the U.S. power market is moving from a market that sells electricity to a market that delivers usable power. The core tension over the next few years is the gap between reliable load demand and the speed at which the power system can expand. Natural gas will bridge part of the short-term gap. Over the medium and long term, power equipment, substations, transmission, distribution, behind-the-meter power, and cooling systems enter a longer construction cycle. The companies worth studying are not necessarily the ones with the loudest theme. They are the ones that can deliver on time, keep being chosen by customers, and retain their position in the next round of projects.